So May-June 2015, P11 and P12 explain how the width of the bus. I told you that width of the bus actually directly translates the amount of data which is being transferred. Higher the number of wires in the bus, better and faster the data will be transferred. Overall throughput will be improved. And then we have got USB and clock cycle, clock speed. Faster the clock speed, higher the transfer rate, better the performance throughout. Throughput will be improved, but one of the disadvantage of higher clock cycle is the generation of heat, and that will actually affect it. And then part B says that most common computers use USBs. What are the benefits of the USB? USB is backward compatible, it is automatically configured, it is plug and play. It cannot allow devices to be wrongly attached, and USB 3 is full duplex. All the standards of USB 1, 2, 3, they all are compatible, and devices can draw power as well through the USB ports via the USB wires. Then May-June 2015 P13. Name and describe three buses used in von Neumann architecture. So we know these three buses are system bus, address bus, and data bus. So address bus lines are used to transfer address of the memory or input-output locations, and it is unidirectional. You have to describe it, it is unidirectional. And then data bus used to transfer data between the processor and memory or input-output devices. It is bidirectional bus. See, there are less marks allocated, so you don't have to write a lot, and you would be writing in bullet points. And then we have got control bus used to transmit control signals. For example, read, write, fetch, and the address of the first instruction of the program. And dedicated bus, since all timing signals are generated, clock is attached to the system using this bus. And then we have got October, November 2015 P11. So we have got this structure in front of you. So what is this? So system clock is leading to control unit and main memory. System clock is leading to control unit and main memory, and you can see that main memory and control unit are attached with this bus, and it is only bringing in data from main memory to control unit, and control unit is also connecting to main memory. So this A is actually, what does it say? The diagram above shows a simplified form of processor architecture. Name the three buses labeled A, B, and C. So this is control bus, since this is attached to the control unit. So this is control bus. B is attached to registers and main memory. So obviously, and it is one way. You have to pay attention to the arrow. So it is one way. So if it is one way, it is address bus. And then we have got something which is attached directly to registers from main memory, and it is two-way. So this is data bus. Now state the role of each of the following special purpose registers used in a typical processor. So program counter stores the address of the next instruction to be executed. Memory data register stores the data in transit between memory and registers. Current instruction register stores the current instruction which is being executed and decode and executes it. Memory data register stores the address of the memory location which is about to be accessed. Since these are four and there are 4 marks allocated, you don't have to write a lot. Just a single solid sentence for every single part. Okay. Now, October, November 15P12. Describe the stored program concept for basic von Neumann model for the computer system. So I told you that whether it is described or explained or whatever, you have to write the whole scenario. Since it is 3 marks, and but still I would suggest that you complete the whole definition. So the answer would be program must be resident in main memory to be executed. That is a stored program. Program consists of the sequence of instructions which occupy a block of main memory. All right, the block of main memory where all the instructions are present, and then that block is having instructions which are adjacent to each other. They are contiguous. Instruction and data is indistinguishable, and they are still in the same memory. Each instruction is fetched and then executed. Instruction fetch and data operations cannot occur at the same time. This is something that you have to remember, that first instruction is fetched and then it is executed. All right. Number 6B, 1. Name the 3 types of the buses used by the system. Processor: control bus, data bus, and address bus. And state the function of the system clock in the processor. It generates timing signals which synchronizes the fetch, decode, execute cycle steps. Now, 2017 P11, October, November 2017 P13. Question 4A. The diagram shows the components and buses found inside a typical personal computer. So what is A? A is just going from itself to B. So definitely B is control unit and A is what? System clock. System clock is actually sending a timing signal to the control unit. So this is actually system clock. This is control unit. Okay. And then what is C? General purpose registers are attached to it, and the data is going from C to general purpose register. So definitely it is main memory. And in new syllabus it is also called immediate access memory, IAS. Now let's see what is D. D is connected between general purpose registers and C, and it is two-way. So D is definitely B. Which bus is this? D. D is actually data bus. Okay. All right. And then we have got what? E. E is coming from main memory to general purpose registers, and it is also in control of control unit, since it is one way, and it is actually not connected. Okay. It is not connected to main memory. It is not connected to main memory. So it is control bus. Since it is two-way from control unit and it is controlling general purpose register, and it is not connected to main memory, it is control bus. So E is control bus. And then we have got F. It is two-way and it is from general purpose registers. So F is data bus. I believe F is data bus. This D is actually control unit to general purpose registers. This D is actually the address bus. F is data bus, D is address bus. So from control unit, it is one-sided. So this is address bus. If from control unit, if it is two-sided, then it should be E is control bus and then we have got F, which is data bus. Yes, it is now correct. Okay, some components and buses only have only have labels. A to F identify themselves. For each label, choose the appropriate title from the following list. The title for the D is already given. Where it is given by? Okay, address bus. Yes. So title for D is address bus. So we were initially wrong, but then we are now correct. Okay. Now, this is once again the same. October, November 2017, P12. Now, A was, everything is connected from memory in A. So this is general purpose registers. General purpose registers. And then we have got B, it is system clock. Then we have got C, since it is only attached to control unit, definitely it is arithmetic and logic unit. And then we have E, it was control bus. And we have got D, it was actually again, this time they would have said it, it is data bus exactly. And this one is control bus. Okay, so now clock speed is a factor that affects the performance of PC. Explain the statement. We have already covered it. Okay, so let's move ahead. May, June 2018, P11. The von Neumann model uses a series of registers. Explain what is meant by the term register. So it is a small piece of fastest memory inside the microprocessor. And it is part of the processor. It is temporary storage. Data is about to be processed, is held in the registers. So explain B1, explain the purpose of memory data register. It stores or holds the data or instruction which is to be fetched and written back, the data obviously. So it is also called the gateway of the microprocessor. So it stores instruction when fetched from the memory, it stores or hold the data when it is being written back to the memory. It is supposed to be the gateway of the microprocessor. The location that is accessed is the address which is in the MAR. The content of that address arrives in MDR. Name two registers other than MDR. So we have got CIR, we have got PC, index register, what other, status register, interrupt register. May, June 2018, P13. A computer is designed using the von Neumann model. Describe the role of arithmetic and logic unit. Arithmetic and logic unit, control unit in von Neumann model. So A is asking for ALU. So ALU performs arithmetic operations. ALU performs logical operations. ALU performs logical comparison operations. Remember CMP? Control unit sends and receives signals, synchronizes operations between the steps of fetch, decode, execute cycle. uh, ex, uh, Input and output of the data is being controlled. And if you would have noticed that this data bus is two-way, but a single bus. So when the data is coming in and also going out, they might collide. So this synchronization of the bus so that the data which is coming in or going out from the microprocessor does not collide. This synchronization is also the part of control unit. Number B, 3B, describe the role of status register and program counter. Status register is having multiple bits, and every bit is interpreted for a different purpose. Every bit is also called the flag. Each flag is set dependent on an event. For example, if there is an interrupt, one of the bit is set. If there would be an overflow, there would be another bit that will be set. If there will be a carry, another bit will be set. Or if there would be a program error like division by 0, there will be a bit that will be set. So that is a status register. Status register is a general purpose register which is having number of bits, and all bits would have a different role. They will be related to different events, and every bit in the status register is also called a flag. And then we have got program counter. Program counter stores the data, it stores the address of next instruction which is to be fetched. And that's about it. Now, October, November 2018, P12. The diagram shows 3 buses and 2 descriptions. So control bus is 2 directional. Address bus is unidirectional, and data bus is bidirectional. I told you when I was teaching you that this is actually something very important that you should remember, that which bus is how many directions. Now, there are descriptions. So basically, what do we have? We have registers and their descriptions. The first description says that it stores the data that has just been read from the memory or is about to be written back to the memory. And it is what? MDR, memory data register. The second one is stores the instruction that is being fetched and executed. So this is current instruction register. It stores the address of the input device from which the processor accesses the instruction. So it stores the address of the input device from which the processor accesses the instruction. We have not read anything like it as of yet, so just wait. Let's see if there is anything. There is no such register which does this. It stores the address of the next instruction to be read. This is program counter. Then it stores the address of the memory location about to be written or read from. This we know that this is MAR. So this thing we have not discussed. So it is not the part of the syllabus. So we are just leaving it. I don't think that this is any of the registers doing. Bringing in data from memory address, that address lies in MAR. But bringing in data from that particular device, where does that lie? In a register we have not read, we have not studied any of the register which is holding the address of the device. No, it is MAR which is holding the address, memory address, not the device address. Part B. Many components of the computer system transfer data between them using buses. One example of a bus is address bus. Name 2 other buses. So we have already done it. State the benefit of increasing address bus width from 16-bit to 32 bits. So If it is 16 bits, maximum address that we can access would be 2 to power 16, that is 65,536 addresses. That is just 65K addresses, not even 1 MB. If it is 32 bits, it is 4 GB that we can access. If you do remember, this is 2 bytes, so 65,536 total addresses that we can access it. If it is 32, this is 4 GB. So we cannot have a RAM more than 65K, but in this case, we may have, for the system which is 32-bit, we can use a memory which is as big as 4 GB. So significant increase in the number of directly addressed memory locations. All right. So if we have got 65K, we cannot access more than 65,536 addresses directly. But if it is 32 bits, we can access as many as 4 GB access directly. So addresses directly. So it means same. If over the data bus we cannot hold more than 16 bits, we won't be able to access any of the memory beyond 65,536 bits. Similar. Okay. Now this is it. This was the part which is CPU architecture. Now let's do 1.4.2. So this 1.4.2 is related to fetch execute cycle. The table shows 6 stages in the von Neumann fetch decode execute cycle. We have to actually sequence them from 1 to 6. So the address contained in program counter is copied to the memory address register. This is 1. And then we have got the last one. The instruction is copied from the memory location contained in the memory address register and placed in the memory data register. The instruction is copied from the memory location. This is 2. The instruction is copied from the memory data register and placed in CIR. This is 3. The value in the program counter is incremented 4. So this is fetch completed and then decoded and then executed. All right, so mind it. First you have to complete decode or fetch and then decode and then execute. The sequence of operations shown in register transfer notation, the fetch stage of the fetch decode cycle. So we have to actually, what is the right sequence? PC increments from MAR receives the data from PC, and then MDR receives the instruction. The instruction from MDR goes to CIR, and then PC increments itself by 1. And here what they have done, that as soon as the data from PC moves to MAR, PC increments itself by 1, MDR receives the instruction, and then the CIR receives the instruction from MDR. Describe what is happening at step 2. I described everything. So let's get down to explain what is meant by an interrupt. Interrupt is a signal from a device or program that requires the attention of the microprocessor. Explain the action of the processor when interrupt is detected. I did explain it thoroughly, but let's just revise it. At a point during the fetch decode execute cycle, after the instruction is executed, System checks for the interrupt. If an interrupt flag is set in the interrupt register, all content of the registers are saved in RAM. PC then loads the interrupt service routine to help deal with the interrupt. Once the interrupt is dealt, all the data for the registers from the memory is called back and the previous program is resumed. May, June 2016, P11 P11 and 12. Describe how special purpose registers are used in fetch stage of the cycle. So you would have to tell that from PC it goes to MAR, PC increments cell by 1, MAR points out to the main memory, from main memory data arrives in MDR, from MDR it goes to CIR, that is the fetch stage. Use the statements A, B, C, and D to complete the description of how fetch execute cycle handles an interrupt. So the processor checks if there is any interrupt. If the interrupt flag is set, then the register contents are saved and the address of the interrupt service routine is loaded into the program counter so that it could help to, since ISR itself is a program, it should be required to be executed. So its first address will be loaded in program counter, and then ISR once completed, it gets back to its original routine. So this would be B, D, A, and C. This would be the sequence, B, D, A, C. At the end of the cycle, the current instruction, at the end of the cycle for the current instruction, the processor checks if there is an interrupt. The processor checks if there is an interrupt. B, the interrupt flag is set. Then data contents are saved and the address of the interrupt service routine is loaded to the program counter, and when the ISR completes, the program restores the register content. The interrupted program continues its execution. A student has written the steps of the fetch stage of the fetch execute cycle in register transfer notation. From PC it goes to MAR, it is wrong. From PC it goes to MAR. Then the content of the PC is incremented by 1. From MAR, instruction arrives in MDR. And from MDR, the instruction goes to CIR. So that is how we will be solving it. Okay. You need to understand that we have to know things by their concept. There is no ratification, no rote learning. You have to understand the concept so that you could answer such questions. One stage of the fetch decode execute cycle includes checking of the interrupt. Give 3 different events that can generate an interrupt. It is, I told you, hardware fault, an IO request, input or output request, or it might be program error or software error, etc. Explain how interrupts are handled during fetch decode execute cycle. We have just discussed it. Move on. From PC, it goes to MAR. The content of the PC is incremented by 1. Then the instruction at the address mentioned in MAR goes to MDR. The content of MDR goes to CIR. All right, the steps shown in part A are incomplete. Write the missing registers. We have done it. The third instruction has double bracket. State the purpose of the double bracket. So the inner bracket shows the address which is in MAR, while the outer bracket shows the content of the memory whose address was inside the bracket, inner bracket. The content of MAR is an address. It is the content that the address which is actually required from the memory, which is inner bracket, and the outer bracket is the content of the address pointed by the MAR in the RAM. Okay, so state the purpose of double brackets. One stage of fetch execute cycle includes checking of the interrupt. State what is meant by an interrupt. So a signal from a device or a software or a source which is telling the microprocessor that it requires attention. The fetch execute cycle is shown in the register transfer notation. There are 3 errors in the fetch execute cycle shown. From PC, it goes to MAR. PC is incremented by 1. From MAR, it goes to MDR. And from MDR, it goes to CIR. A program is written in assembly language. The processor handles interrupts within the fetch decode execute cycle. Give one example of the hardware interrupt and one example of the software interrupt. So this is May, June 19. So hardware interrupt is printer out of paper. Out of paper. No CD in drive. Etc. This is hardware. And software interrupts are a running program that needs input. Program needs input. And second might be a program error like division by 0, etc. Explain how the processor handles the interrupt. We have already discussed it. So this is fetch decode execute cycle related past paper questions. Let's do the next task. So this one is 1.4.3, the processor's instruction set. 5 modes of addressing and 5 descriptions are shown below. Draw a line to connect each mode of addressing to its correct description. So let's just read the description and then see what it is. The operand in the address of the register. The operand is the address of the register. So this is indirect. The next one is the operand is the address of the value to be used. So this is direct. Third one is the operand is the offset from the current address where the value to be used. The operand is the offset from the current value. So how many times you have to move forward to get the data, that is relative. The operand plus the contents of the indexed register. So this is actually indexed. The operand plus the content of the indexed register is the address of the value to be used. So this is indexed. The operand is the value itself. So this is immediate. You have to have a good knowledge of it. All right. So next question. Describe what happens to the registers when the following instruction is executed. It is being executed. It is already fetched. It is in CIR. So first of all, this part would go to MAR. So MAR would have 35. All right. The accumulator afterwards will be loaded whatever the data that is present at the address 35. So this is load direct. That's about it. You would have to write something like the MAR is loaded with the operand of the instruction, which is 35. The accumulator is loaded with the content of the address held in MAR, which is 35. That's it. That is what you have to tell. The following diagram shows the content of the section of memory of the indexed register. So this is 2017 P11 and P13. So LDM 500. So this is direct. So accumulator would have 500. LDD 500. What is that? 500? 496. So this would be loaded. LDX 500. So index register has got 3 in it. So 500 plus 3, 503, 502. So now LDI 500. 500 says go to 496. 496 is having 86. So this is indirect. The following diagram shows the content of the section of the main memory and index register. LDD 355. So what is that? 355, 351. This is direct. LDM 355. So there we go. 355. LDX 351. So 124. So index register has got 6. So 351 plus 6. 1, 2, 3, 4, 5, 6. 22. And then it says LDI 355. So 355 says 351. Go to 351, it says 86. This is indirect. What is meant by direct addressing and indirect addressing? Direct addressing is basically when we go to the address that is given directly to us. The operand is the address and where the data is stored. And indirect addressing where the operand is the address of the data where the data is stored. So what we have to do, the operand is an address. The address holds the address of the data. Part B. Explain how the instruction add 20 can be interpreted as either direct or indirect. So this is direct. Can be interpreted as direct or indirect. So if it is direct, then the data from the address 20 will be loaded, will be added to the accumulator and saved to the accumulator. If it is indirect, then system go to address 20, find what address is there, and from that address find the address of the data and then that data will be added to the data in accumulator and saved there. So either direct or indirect. So if it is direct, then 20 is the address of the data. If it is indirect, 20 is an address which holds the address of the data. Now part B. Part B says the assembly language instruction in the following table uses either symbolic addressing or absolute addressing. Symbolic addressing where we use the names or the symbols, absolute addressing where we use the number. So this is absolute, this is absolute, this is symbolic. This is address, this is address, this is symbol, label, or you may call it label. So these are addresses, and this is called label. State question number 3, October-November 2018. Question 3b. State what is meant by index addressing. The address to be used is found by operand plus the content of the index register, which is offset. Immediate addressing, the operand is the value itself, and that will be loaded directly to the accumulator. State what is meant by relative addressing. This is October-November 2018 P13. The relative addressing is actually the operand is the offset to move from the current instruction's address to that particular location to fetch the data. So a number, the offset is added to the base address, all right, to the given address. And index addressing, the content will be added to the content of the index register, which is offset, and the final register is obtained to have the data. Show the result of the general purpose register X after the following instruction is run. The content of the register X will be increased by 1. We don't have, I must have copied the content of index register, register X. Since I don't have, let's say register X was 000000111. So this is 7. So if we increase it, it would become 8. All right. So this is the effect of increase. So if it was 7, it has become 8 after the increase. Now, the processor instruction set can be grouped according to their function. For example, one group is the modes of address. Identify 2 other groups. So we had how many groups? We had data movement group that we have studied. Then we have input and output group. Then we had arithmetic operations group. Then we have compare instructions, comparison group, and then we have jump group, jumping group. That's about it. A processor instruction set can be grouped according to their function. We have done it. May June 19 P13 program is written in assembly language. Assembly language instruction can be grouped by their purpose. This is what we have done. Let's see what they say over here. LDR, this is loading. So this is basically data movement group. LDR. What is LDR? LDR is actually load to the index register. LDR. So this is data movement. Add, arithmetic. Jump, JPN, jump if not equal. Decrease, arithmetic. Okay. Von Neumann is an example of computer architecture. All right. The following statements describe feature of the low-level language. Complete the statement by writing the appropriate term. Dash is a sequence of instructions that are given and identify these instructions may need to be executed several times. Basically, this is macro, but this is not part of the syllabus 9618 anymore. Okay, so do not worry. Macro, I have not taught to the latest 9618 syllabus, and this is not part of the syllabus anyway. A dash is an instruction that tells the assembler to do something. So this is directive. Again, this is not part of the 9618, but it is part of 9608. So new students, do not worry. The processor instruction set can be put into several groups. So we can name these groups data movement group or whatever. This is part of your syllabus, so don't ignore it. And there are several others. Okay, October, November 2019. We have to tell the addressing mode from the address by adding the given number of base addresses. From the address by adding the given relative. Load the content of the address held at the given address. This is indirect. Load the content of the given address to the accumulator. This is direct. From the address, form the address from the given address plus the content of the index register. Indexed. Load the given value. Immediate. So that's about it. The last part, 1.4.4 assembly language, and I believe that we have already completed it, assembly language. Let's see. When we were doing the topic during the lecture, we completed assembly language, and I also shared with this document with you. Let's see. One 1.4.4, the last part, assembly language. Assemblers translate from assembly language to machine code. Some assemblers scan the assembly language program twice. There are therefore referred to as two-pass assembler. The following table shows 5 activities performed by two-pass assembler. The following table shows 5 activities. Write 1 or 2 to indicate whether the activity is carried out during the first pass or during the second one. So, any symbolic address is replaced by an absolute address. That is second pass. Any directives are acted upon. Any directives are active upon. This is 1. Any symbolic address added to the symbolic address table. This is pass 1. Data items are converted into their binary equivalent. 1. Forward referencing are resolved. 2. Okay. This I tried explaining, but you see, to the extent they will ask, we never know. Solving past paper is always a good idea because it will clear your concept furthermore. ठीक हो गया? Now, The diagram shows the content of the memory LDD 121. So this at 121, 0101 will be loaded. Show the content of the accumulator after execution of the instruction LDI 124. So 124 is actually 127. So go to 127 and we have got this 0110 1001. This is indirect, so that is how it works. Explain how you arrived at your answer. So you would have to tell that when I went to 127, it had, sorry, when I went to 124, it had 127, and then I went to 127 since it is indirect addressing, and I'll pick up the data from address 127. So index register is 6, 1, 2, 4. Okay, so it is 6. LDX 120 means 120 plus 6 becomes 126. So you go to 126 and you find what? 0100000001. So 01000001. That is what you have. Trace assembly language program using the trace table. We have done such questions, so I'm skipping such questions. Index register is 8, 1, 2, 4, and 8. So LDX 60 becomes 68. So at 68, we have got this 01000101. Decrease index register. So index register was 8. So if we decrease it, it would become 7. 1, 2, 4. 4 plus 2 plus 1 is 7. Okay, so this is decreased. We solved this question while we were doing assembly language. During the lectures, we have solved such questions. Oh, let's see if we have got anything different, then we will definitely be solving it. Computer scientists often write binary representation in hexadecimal. If you do remember from O-level, it used to say that they are less error prone and can be remembered, things like that. A second instruction has been written in hexadecimal form as 053F. Write the equivalent assembly language instruction with the operand in denary. Opcode is 05. So 05, we have to check what is 05. This is 5. 05. So this is LDI. So this is LDI, and this is 3F. So 3, 1, 2, 4, 8, and F, 1, 2, 4, 8. So this is F, which is 15, and this is 3. So this is 1, 2, 4, 8, 16, 32, 64, 128. So this is actually 63. So this is LDI 63. This is the instruction that we have. This is hex of it, and this is ordinary instruction. LDM67. So you have to write the machine code. So what is the machine code for LDM? 00010010. And what this is? 67. 1, 2, 4, 8, 16, 32, 64, 128, 67, 64, 567, 567. So this is your machine code LDX7. 7 is this. How do we know that we have got 7? Because this is immediate addressing. LDX is this 0001 0010. So this is easy. Now we know about it. 1640. So 4 is 12480100, and D is A, B, C, D, E, F, 10, 11, 12, 13, 14, 15. So D is what? 30. So 1, 2, 4, 8. 8 and 4, 12 and 1, 13. So this is 4D. What is 16? You would have to check. 1, 2, 4, 8, 16. This is actually 1, 6. Sorry. This is hexa. So 1, 6 would be this. This is 1. This is 6. LDR. 16 is LDR. 4D is 1, 2, 4, 8, 16, 32, 64. So this is 64 plus 8 plus 4 plus 1. 77. LDR 77. And maybe you would have to put this because it was part of this deal. This question we already completed. This is 2 past question that we have completed while the lecture was going on. This macro and directive is no more part of 9618, so leave it. This we have already completed. This question is completed during the lecture. Watch lecture again if you like to. Lecture number 7. Okay, and solve these questions for your practice, for God's sake. Now, May, June 2019, P11, simple program written in assembly language translated using 2-pass assembler. Program for 2-pass assembler. This is which year? 2019. So, now, creation of symbol table is always the part of first. Expansion of macros is actually first. Generation of object code is second. Removal of comment is first. All right, so you have to collect this data so that you could prepare for your exam. A program is written in assembly language. The opcode LDM and LDD are used to load the register. The opcode LDM uses immediate addressing and LDD uses direct addressing. Describe what happens when the following instructions are run. Accumulator will be loaded with 300 and accumulator will be loaded as it is direct, whatever at the 300 address. Okay. So this is it for assembly language. Now let's solve few of the questions for bit manipulation. Bit manipulation to monitor and control devices. This is the last part of the past paper solutions. The equipment records temperature in the greenhouse. It does this for 7 locations. Each recording is stored as 2 successive bytes. This is May, June 15, P31 and P32. The format is shown below. Greenhouse location 0, 1, 2, 3, 4, 5, 6, 7 and temperature reading in byte 2. The location is indicated by the setting of one of the 7 bits in byte 1. For example, location 4 is indicated by setting bit 4. If you do remember, we were setting using OR gate, we were clearing using AND gate, and we were inverting using exclusive OR gate. The location is indicated by setting one of the 7 bits in byte 1 here. For example, location 4 is indicated by setting bit 4. Bit 0 of byte 1 is acting as a flag. When the reading has been processed, it is set to 1. All right. Byte 2 contains temperature reading 2's complement integer. So this would be negative as well as it would be positive because it is in 2's complement form. So if we mark it 1, 2, 4, 8, 16, 32, 64 and minus 128. So interpret the data that is in below. So location 5 indicates that the data is changed and the 0 bit is saying that the data is processed and the temperature at location 5 is 16 plus 8, 24 degree. All right. So the system receives temperature minus 5. How would you come up with minus 5? So 1, 2, 4, 8, 16, 32, 64, minus 128. So this is plus 5. So to the first one from the right, keeping everything same and toggling the rest. So this is minus 5. Okay. So this is minus 5. Degree from sensor 6. So sensor 6 is set. Let's see if it is processed or not. Data has not yet been processed. So this would remain 0. Get the idea? So the accumulator is loaded with the value of byte 1 from location 106. Write the assembly language instruction to check whether the reading in byte 2 came from the location 4. This is D1. The accumulator is loaded with the value of byte 1 from location 106. So that will be added. All right, load 106, write the assembly language instruction to check whether the reading in byte 2 came from location 4. 0, 1, 2, 3. So this will be ended. For checking, it is always ended. Then it is what? Remember, bit mask, it is in binary form. And for the bit 4. So 0, 1, 2, 3, 4, 5, 6, 7. So this would be your bit mark. All right. So you can write it in the form 1, 2, 4, 8, 16. or in the form, if it is hexadecimal. So this is hexadecimal 16, this is denary 16, this is binary 16. You can write any of these. Okay, so we have checked it. So we use AND for checking or for setting, exclusive or for inverting. May, June 2015. P33. Each greenhouse has 8 sensors, 1 to 8, 1 to 8. The byte at address 150 is used to store 8 1-bits flag. Here, a flag is set to indicate whether its associated sensor reading is waiting to be processed. A flag is set to indicate more than one sensor reading may be waiting to be processed at any particular moment. Data received from the sensor is stored in a block of 8 consecutive bytes, 201 to 208. The data from sensor 1 is at address 201. So this is sensor 1, 2, 3, 4, 5, 6, 7, 8. These are sensors. Interpret the current reading from sensor 2. Interpret the current reading from sensor 2. This one, sensor 2. So this says that reading available for processing, reading value is 4. Reading value is 4 and it is available for processing. This is what it means. A flag is set to indicate whether the associated, all right. This is waiting for processing. Number 2, accumulator is loaded with the data from location 150. So this is LDD 150. Write assembly language instruction to check whether the data, there is a value waiting to be processed for sensor 6. So from sensor 6. So which one is sensor 6? 1, 2, 4. So this would be 0, 0, 1. So this would be AND this is 4. All right, that's it. अगर आप इसको बाइनरी में लिखना चाहते हैं तो then बाइनरी का 4, 1, 2, 4, 8, 16, 32, 64, 128. And if you like it in hexa, then it is 4. Or maybe in hexa you would have to write 0, 4 because you have to complete the byte. May, June 2016, P3132. An intruder detection system for a large house has 4 sensors. An 8-bit memory location stores the output from each sensor in its own bit position. The bit value for each sensor shows 1, the sensor has been triggered, 0, the sensor has not been triggered. The bit positions are used as follow, not used. So if it is sensor 1, 2, 3 or 4, and if it is not used, then it would be 0. And it means that the part of the byte over here is not used. Okay. All right. What they want? Part of assembly language code. So it says that this is sensor location, this is label. This is count location, this is value location. So loop starts, load sensors. So what is that sensor? Sensors has B 1 2 3 4 1 0 1 0, and then it says that end it with the value. So 0 0 0 0 1 0 1 0, we have to end it with the value. So what is value? 1. This will become 0 1 0 1 0 0 0 0. So accumulator would have the same once again. So here, so this would be B 0 0 0 0 1 0 1 0 again. So now it is loaded into accumulator, load sensors, B 1 0 3 4 1 0 1 0, ended with the value, remains the same, ended with the value 1. So 1 2 3 4 1 0 1 0, ended with the value 1. So they all will become 0. So it becomes 1 2 3 4 5 6 7 8 zeros. Compare with 0, it is compared, it is true. Jump if equal to 0. So we jumped here at 0. Load value. So what is that value? 1. So this will be loaded. 1 2 3 4 5 6 7 8. This will be loaded, sorry, not here, but here. So this will be loaded, or you may write it in denary form that it is loaded 1. Compare with 8. So this is false. Jump if equal to exit. So it won't work. Add value. What is value? 1. So 1 plus 1 become 2. So what we would have now? 0 1 2 1 2 3 4 5 6 7 8. Or you may write 2 over here. Then we have store at value. So value would become now 2. Jump to loop, and we will get back to loop, and you would have to complete it until it becomes equal to 8. All right, so complete it. See if you could do it properly. You would have to perform such operations. The operand of the instruction, labeled test is missing. State the missing operand. State the missing operand. Basically, missing operand जो होगा इसका ये आपको जब आप when you will solve it, you would come to know. I have no idea of it. Number 3, the intruder detection system is improved and now has 8 sensors. If you do remember, over here they said that 4 of the bits were empty. All right, so the number that we were using was this and this. Now, if these are 8 registers, it means that this would be sensor 5, 6, 7, and 8. This is what they mean. So they say the intruder detection system is improved and now has 8 sensors. One instruction in the assembly language code will need to be amended. Identify the instruction. Identify this instruction, write the amended instruction. Let's see which instruction this could be. See, this is compare with 8. So this was 0, 0, 0, 0, 1, 0, 0, 0. So this is 8. Now when this one will go over here, this would become 1, 0, 0, 0, 0, 0, 0. So this would become compare with 128. All right. So this would be the instruction that will be identified. Identify the instruction. Compare with number 8 because it was the 4th bit. Now we would have to compare at the 8th bit. So this would become compare with 128. A museum stores antique items. So I'm just leaving this question for you so you could complete it. All right, so that's about it. All of the questions, everything from this lecture, this was the last part. Everything is completed. I tried solving all of the questions.